Okay, this is video 25.6. We're going to be looking at how conductors and electric potential work together. Now, we've seen conductors before. They allow charges to move. We also know that any excess charge on a conductor goes to the surface because that charge wants to get as far away from itself as possible. And as a result of that, the electric field inside the conductor is zero everywhere. Now, we need to ask what this says about potential. Remember, potential is equal to the integral, or change in potential is equal to the integral of E dot dx. But if E is zero everywhere, then delta V will also be zero. And that means that the potential is uniform inside a conductor. And that's something that's very important. You need to be able to explain why that is. So if we have a spherical conductor, so a ball of radius capital R, what does the field and the potential do to that? Well, Gauss's law, so let's say we've got charge of plus Q on it, which resides on the edge. Gauss's law says that if you draw a spherical Gaussian surface around it, the enclosed charge Q divided by epsilon 0 equals the surface area of that sphere, where that radius is little r, times the electric field, and the electric field ends up being the same as the field for a point charge located at the center of the sphere. But that is for r greater than big R. For r less than big R, i.e. inside the conductor, the electric field is zero. Because of the way in which we calculate potential, we take an integral where we start at infinity and come into a distance r. The result of that is that v equals 1 over 4 pi epsilon 0 q over r for r greater than big R. Because the electric field outside the sphere is the same as the field of a point charge, the electric potential outside the sphere will be the same as a point charge. But then, because the electric field is zero inside the conductor, the potential stops changing, and so the potential inside the conductor is the same as the potential at the edge of the conductor. And so it becomes 1 over 4 pi epsilon 0 q over big R for r less than big R. And that's an equation that you should know where it comes from and probably memorize it. And that's all very well and good, but let's see what happens if we take two spherical conductors, radius r1 and a smaller one with radius r2, and we connect them with a wire. Now, the result of connecting them with a wire is that charge can spread out between them. And the charge will keep moving until the potential, V1, is the same as the potential V2, because now they're effectively one big conductor, and that means their potentials have to be equal. And that means that if we look at the charge on, let's call that Q2, and the charge here is Q1, K times Q1 over R1 equals K times Q2 over R2. And the result of that is that Q1 over Q2 equals R1 over R2. So not surprisingly, the larger sphere has more charge than the smaller sphere does. But if we look at the charge density, so the surface charge density, where sigma is equal to so sigma 1 is equal to Q1 over the surface area of the first sphere, and sigma 2 is equal to Q2 over 4 pi R2 squared. If we look at that ratio, sigma 1 over sigma 2, that's Q1 over Q2 times R2 over R1 squared. And that means, because Q1 over Q2 is R1 over R2, the sphere with the smaller radius has a larger charge density than the sphere with the larger radius. So there's more charge on the larger sphere, but because it also has more surface area, the charge density on the small sphere is larger. And in general, when you have an irregularly shaped conductor, if you have sharp points, they're going to have a lot of charge that gather on them. And that's, we'll see in the next slide, that's how lightning rods work, and why they prevent your house from getting struck by lightning. But you do need to know that when you connect two conductors, the charge density on the smaller one is larger. And now let's look at the electric field near the surface of a conductor. So here's the surface of a conductor. It has charge density sigma, and we want to know what the electric field is right outside the surface. Now the first thing we'll say is that we'll remind ourselves that V is uniform in a conductor. And that means that the surface of the conductor is an equipotential, which in turn means that the electric field near the surface is perpendicular to the surface. So if we draw the electric field here, it's always perpendicular to the surface of the conductor, and the electric field inside the conductor is 0. So what we'll do is we're going to approximate this as planar symmetry, and we'll draw a Gaussian surface that goes through the surface of the conductor. So part of the Gaussian surface is inside the conductor, part of the Gaussian surface is outside, and we'll say that the area of the end cap of that surface is A. Now Gauss's law is going to tell us that the enclosed charge is equal to the total flux through the surface. That enclosed charge, though, is equal to the charge density times the enclosed area. And the flux through the curved side of the cylinder is 0, because the field is parallel to the surface. The flux through the bottom of the cylinder is also 0, because the field inside the conductor is 0. And the flux through the top is just equal to the electric field times the area of the top. And so when we put all that into Gauss's law, that integral EdA just ends up equaling E times A. The enclosed charge is sigma A over epsilon. Divide both sides by A, and we find the electric field just outside a conductor is equal to sigma over the permittivity. And that holds for any conductor, regardless of shape. Because if you get close enough to any surface, it starts looking like a flat surface. The result of this, if we go back to the previous slide, is that the smaller radius conductor with a large charge density will have a larger electric field just outside it. And if the electric field gets large enough, what happens is electrons just start leaking off the conductor into the air. And so if you have a sharp point on a conductor somewhere, electrons will leak off of it, and it will prevent the buildup of too much charge on that conductor. That's how lightning rods work. They cause electrons to leak off into the air slowly, rather than building up until there is a lightning strike that burns down your house. So you should be able to explain, based on the properties of conductors, why everywhere in the conductor has uniform potential, and for a spherical conductor you should be able to calculate that potential. You should also be able to calculate the field just outside a conductor. Tomorrow I'm going to be checking problems 50 and 51.